Hi, I'm going to start this problem now. How many 5-digit positive integers exist where the digits are non-increasing from left to right? For example, 87,743 and 10,000 fulfill these conditions, while 78,987 and 33,429 do not. Okay, well, what do they mean by non-increasing? Let's first think about this. Well, by non-increasing, it looks like they're talking about non-strictly decreasing integers. What I mean by that is, like, mathematically, a decreasing sequence. A decreasing sequence is defined by decreasing sequence, which is also called non-increasing sometimes, is defined by some sequence where we have the initial term a0, which is greater than or equal to the next term a1, and greater than or equal to ... greater than or equal to an, right? Basically, every element of the sequence is greater than or equal to the element that comes after it, right? Meanwhile, something like a strictly decreasing sequence would be of the form a0 is greater than a1, which is greater than ... which is greater than an, right? So there's a difference, right? We don't have strict inequalities in this former case. So that's why this problem is a little bit difficult, right? Because they're asking about non-increasing, which means there could be duplicates, right? If they were simply asking about strictly decreasing, there would be an easy solution, right? This is a common problem, right? So how would there be an easy solution? Let me explain that to you, right? Well, first, so let's say that we have our sequence a0, which is greater than a1, which is great. So let's pretend that this problem was different, right? Instead of that, we're going to pretend that instead of asking for non-increasing, let's do the same problem, but let's just say it's asking for strictly decreasing, strictly decreasing. So let's pretend it's a strictly decreasing set of positive integer, 5-digit positive integer, and we have a0 is greater than a1. So a0 would represent, in this case, the 10,000th place. A1 would represent the 1,000th place, and a2 would represent the 100th place, and so on and so forth, right? So these digits would actually make up the 5 digits of the number, right? The elements of the sequence could be combined to make the actual 5 digits of the number, right? So in this strictly decreasing case, what we can do is we could just find any 5 distinct integers, and there always exists exactly one strictly decreasing sequence. So for example, we are dealing with the set from 0, 1 through 9 inclusive, right? The set of positive integers from 0 through 9. Why? Because those are the only possible digits we can have. So we're dealing with this set. We're choosing a0, a1, and so basically we're choosing ai is within this set, 0 through 9. AI is within the set. We're choosing all of these elements separately from the set. So if we want to choose 5 distinct elements, and they have to be distinct in order to form a decreasing sequence, if we want to choose 5 distinct elements, all we have to do is choose 5. Now, let's say that we chose, just for argument's sake, let's say we chose 2, 7, 6, 3, and 0, or let's say 9, 0, right? There exists exactly one strictly decreasing sequence, right? 9, 7, 6, 2, 0, right? There always is exactly one strictly decreasing sequence. Why? Because there's always exactly one greatest integer, exactly one second greatest integer, and so on and so forth, right? So there's exactly one ordering from in a decreasing order, a strictly decreasing order for any 5 distinct positive integers, right? So that's why our answer to this problem, this reduced problem, where if they were asking decreasing instead of non-increasing, we could have the answer very quickly, which is just 10 choose 5, right? We're just choosing 5 out of the 10 possible digits. We just choose 5 of the digits, and there's only one arrangement for any of the combinations. There's only one arrangement. So the number of solutions is actually just 1 times 10 choose 5. There's only one arrangement for every solution. So it's equal to just 252. Unfortunately, our problem is not that simple because we're dealing with non-increasing sequences or non-strictly decreasing sequences, right? So it's not as easy. We have to deal with the problem a little bit separately. We have to tackle it a bit different. So we want to find, hopefully what we can do is take what we did from this problem, right? So we did a good amount of work on this problem. Hopefully what we did on this problem, hopefully we can use this insight for tackling the real problem, right? So let's move to the side. And let's try tackling the real problem. We have 5 digits again. So a0 is going to be, we have the 5 digits, a0, a1, a2, a3, a4. and this is going to be our number, right? A naught is the 10,000th place, while A4 is the first ones place, right? We have that A naught is not strictly greater than, but just greater than or equal to A1, which is greater than or equal to A2, which is greater than or equal to A3, which is greater than or equal to A4, which is greater than or equal to, well, it's greater than or equal to 0. And also 9 is technically greater than or equal to A naught. And we want to relate this to that original case, right? Because we can't do this that pattern, that cool trick where we just choose the numbers, because the numbers can't be distinct. We know that we can have duplicates, so we can't just choose 5 numbers, because there can be duplicates. So there's going to be more than 252 solutions, that's for sure. We want to relate this problem to that problem earlier. So how do we do that? Well, we notice that if A4 is greater than or equal to 0, A4 plus 1 is greater than or equal to 1, which implies that A4 plus 1 is greater than 0. And why is that useful? Is because we converted this strict inequality into a, we converted this inclusive inequality into a strict one, right? Let's try doing that similar logic to the next one. A3 is greater than or equal to A4. Well, that implies that A3 plus 1 is greater than A4, right? Or A3 plus 2 is greater than A4 plus 1. And that's exactly what we have here. Okay? So we can kind of continue this pattern, right? For example, A2 is greater than, A2 plus 1 is greater than A3, right? It's strictly greater than A3. So if we add 2, then we have A2 plus 1 plus 2 is A2 plus 3. So we can just continue this pattern, A1 plus 4, A naught plus 5. And there have to be strict inequalities because we're adding 1 to each of them. And the reason we're adding 1 instead of, like, for example, 0.01 is because we're dealing with integers, right? So adding 0.01 would be a useless inequality, while adding 1 is actually useful. Now we actually have a good amount of information, right? We actually learned a lot about this problem. We know that 15 is greater than all of this. So what we've done, effectively, is converted this inclusive inequality into a strict one, right? We started from a inclusive inequality, and we ended up with a strict inequality. So 15 is greater than A naught plus 5, and so on and so forth. And this looks familiar, right? This looks exactly like that problem we were doing earlier. This is exactly the same as that problem where we had the 10 digits, right? This is exactly the same problem, right? We were bounded between 0 and 10, or this was greater than or equal to 0, and this was greater than or equal to 9. And there's only 10 numbers. Now there's 14 numbers. But it's the same exact thing. We have strict inequalities. So now we could use that same thing. It's like correspondence almost. So our answer should just be 14 choose 5, which is 14 times 13 times 12 times 11 times 10 divided by 5 times 4 times 3 times 2. You could cancel these out, cancel those out, and we're left with 182 times 11 is equal to 2002. So 2002 is 14 choose 5. Is that our answer? Well, not exactly, because we have to make sure to count for the edge cases. For example, we can't have any sequence of any five-digit positive integer that starts with 0, right? Let's say it was like 0, 2, 4. This is not decreasing, but let's say we had this. Then this would be a 3-digit positive integer, right? Or a 4-digit positive integer, right? So we have to make sure it doesn't start with 0. So let's look at the restriction. If it starts with 0, how many solutions do we have that start with 0? Well, there's 1, right? Because 0 is greater than or equal to 0, which is greater than or equal to 0, and greater than or equal to 0, and greater than or equal to 0. There's only one possible solution, because you can't have 1, for example, because 1 is greater than 0. We can only have equivalent solutions. So we can only have 0 followed by 0 followed by 0. So there's actually only one case we're missing. Only one case we're missing. So we've overcounted, rather. So we've overcounted this one case, and we have 2001 rather, right? Because again, to reiterate, when we're doing this counting solution, we're still counting the cases where 0 is first. We're counting any possible of the solutions, but we don't want all of the solutions. We want any of the positive sequences that can be formed into a 5-digit integer. So the moral of the story is try to simplify your problem to begin with. For example, we simplified this into a strictly decreasing problem, and if you simplify a problem into a simpler problem, then you can relate that to the original problem, and you can solve the original problem much easier. So thank you. I hope you enjoyed the solution, And